to our final keynote of this year's Smalltalk Solutions. There is a change, which hopefully everyone has figured out by now, that originally we were scheduled to have David Simmons from Microsoft talking to us about JavaScript and cloud computing and those sorts of things. He had to drop out at the last minute, and so as a replacement, we have Alex or Alessandro?
Either one.
Okay. We have Alex or Alessandro Warth, both and, a pair presentation. And he's going to be talking to us about his research work with OMeta, something some people may have seen a little bit about at the UPSLA Dynamic Language Symposium last year, I think. So, thank you, Alex. And Alex.
Thank you. On behalf of both of us. So thanks for asking me to do this. I'm honored. And so I guess we know what this is about already. I'm going to talk to you about implementing programming languages with OMeta. And so first of all, I want to give you a little bit of context and kind of tell you a little bit about myself. You probably have worked out that I'm not David Simmons. And I'm not Billy Idol either. That's nice. I'm a researcher at the Viewpoints Research Institute, and I'm a PhD candidate at UCLA. And my area of research is programming languages. And the project that I'm working on is called Steps Toward the Reinvention of Programming. And in case you haven't heard about this thing, the goal is to create a highly useful end-user system, including an operating system, a programming environment, including compilers, debuggers, that kind of thing, applications, or perhaps something better than applications, things like graphics, sound, printing, basically everything that we consider to be personal computing. And we want to do all that in under 20,000 lines of code. And just to put things into perspective a little bit, Windows XP is about 40 million lines of code. And Squeak, even Squeak, which is considered to be small for what it does, is about an order of magnitude bigger than what we're shooting for. And so, why is it that we're starting out this crazy project? And so one of the reasons is that we would like to put people in charge of their own software destinies in the same kind of way that Smalltalk and Squeak and these projects have done in the past, but perhaps in an even bigger way. So obviously no single person can really understand 40 million lines of code, but you can pretty much own 20,000 lines of code, right? So 40 million lines of code is pretty much a library, maybe 20,000 books or something like that. It's really hard to have a good grasp on all of that material. But 20,000 lines of code is just, say, a 400-page book. So it's not that bad. You can imagine mastering that much code. So it's kind of a power to the people kind of thing. Because if you don't like something about the system, well, it's only 20,000 lines of code, so you can go ahead and change whatever it is. You can take the time to understand the part of the system that you didn't like and make whatever changes you want to make. Or better yet, get a couple of your friends together and rewrite the whole thing from scratch. Maybe you could do a better job. It's all about empowering people. And so, because when I look at a big project, something like Windows or even certain parts of Squeak, I get a little discouraged, right? There's so much code, and it's kind of, do I want to spend weeks and weeks learning about how this stuff works, or do I just want to start from scratch? So hopefully this project will help a bit there. And so we also believe that there's a lot of didactic value in this project, because if you take the whole system, this 20,000 lines of code, you could imagine it being this great curriculum for university students to learn about things like architecture, because we're definitely going to have to do a good job with the architecture in order to fit everything into 20,000 lines of code. And also, presumably, we're going to have lots and lots of powerful ideas in there. I mean, after all, we have people like Alan Kay, even Pumata, behind this. And so, and who knows, maybe this curriculum, or part of it, will even be good for AP computer science instead of using dreadful things like Java, or making the students feel like they can't do anything on their own. So you can pretty much understand that the STEPS project is mostly, I mean, it's a big deal of the STEPS project is about code size and understandability, probably the whole thing. And so, as we all know, the choice of programming language can have a huge impact on both of these things. So, what is the right programming language for STEPS? And is there a single programming language that might be good for the whole system? Or maybe should we be looking at multiple little, or smaller programming languages, maybe some domain-specific languages that will be good for parts of the system? So the answer is we really don't know. And so the only way that we can find out is to experiment with lots of new ideas and designs for programming languages. And to programming languages geek like me, it's like Disneyland. I mean, I have all the opportunity to do all this stuff. So, but like this, you have this problem where, so at Disneyland you get there and you're all excited, but you have to wait in line for, say, an hour, and then the rides only take like 2 minutes. So there's a similar problem here in programming language implementation because it takes a really huge amount of time and effort to build a programming language. And this kind of limits how much experimenting you can do with this kind of stuff. I didn't even say that it was, but the NSF is one of the funders of this project. So this time to implement programming languages can be a pretty huge limiting factor for us. And so, and besides, another problem that these programming language implementations, at least the ones that are done traditionally, using conventional means that I'll talk about in a little bit, is that they're pretty big. And so, I mean, if we only have 20,000 lines of code for the entire system, then we really can't afford to spend most of that, most of the lines of code implementing the programming language that we're going to use to build the system. So, so we out to find a way to implement programming languages that was quick, easy, that required very little to be written. That's how OMeta came up. It says OMeta. More specifically, OMeta is oriented language for language. We're going to get into it later, but first, I guess it's probably a good idea to show you a few things that I've built using it. And I'll show also other people have built. Okay, here are a couple of screenshots of a JavaScript implementation that runs on top of Squeak. And the whole thing is about 350 lines of code. And it's all written in OMeta. And this includes a parser, a visitor for dealing with JavaScript's funny scoping rules, and also the code generation. And by the way, this compiler doesn't generate Squeak bytecodes. What it does is it rather generates Smalltalk code. But the thing is, it's not the kind of Smalltalk you would ever want to write by hand. And this kind of gets back to what I wrote about in the abstract for this talk. But I guess we can talk about that later when we get when the flame wars start. So, but this approach of generating source code, targeting source code instead of bytecode or say assembly language or machine language, is known as source-to-source compilation. And we're going to talk a little bit more about this later. But so you can see these JavaScript programs on the left-hand side are being used to control Warth to do some drawing. And then on the right-hand side, we have a Tetris game that was also written in JavaScript. So all this stuff works on top of Squid, and you can actually download it from the web page and try it out for yourself. So OMeta is actually available for a bunch of different platforms. And there's one implementation that's available for Cola, which is a new platform that BNP Martin is developing for Steps. It is another one of my colleagues at Viewpoints Research. And so this is a screenshot of that JavaScript implementation running. And the code that it's running is an early version of Dan Engel's lively code. It's not as lively as the new version, but so this is about, I think, 3,000 lines of JavaScript, and it's doing some pretty Squeak-like things. And you can see that, by the way, this JavaScript implementation is pretty much the same implementation that I showed you for Smalltalk. And so it's also about 350 lines of code. And you can see that even things that people consider to be kind of tricky to do, like you see the bottom right-hand corner, you have some program in JavaScript inside a morph, inside a text morph. And that can be evaluated on the fly to generate that spiral that you see. So this is a pretty realistic JavaScript implementation. We've also kind of experimented with some different ideas for programming languages. So one of them has to do with Prolog. And so my wife is an actress, and she really doesn't know anything about programming. Anything that doesn't look like English turns her off right away. And the same thing goes for a lot of kids, actually. And so Prolog can be such a great vehicle for teaching things about logic and all kinds of powerful ideas. But if it looks scary, people, it's unlikely that these people are going to use it. And so Alan Kay had this idea to make a front end for Prolog that we call Toylog. And this thing runs on top of Squeak, and it allows the end user to write Prolog programs in a way that, I mean, you can see here the programs are pretty much written in English, right? So and this language was implemented in about 70 lines of OMeta code. And so you can see here, I have a few facts in the system about the Simpsons family. So I'm saying, okay, Homer is Bart's father, Marge is Bart's mother, and then I'm teaching the system what parent means. So X is Y's parent if X is Y's father or X is Y's mother. And then I'm asking, X is Y's parent. Who is, sorry, X is Bart's parent. So who is Bart's parent? And so I'm going to do a tiny little demo for you, and then we'll get back to the schedule. Let's see. Okay, so this is Squeak, and this is the definition of a rule for grandfather. So X is Y's grandfather if X is Z's father and Z is Y's parent. And so I showed this to my wife, and she actually understood it. It made me pretty happy. It's a first. And so we have a bunch of these facts and rules that we wrote using the browser. And here are a bunch of questions that we can ask the system. And so here's a question, or I'm asking the system to verify this. So Homer is Bart's father. So if I say do it, it says yes, Homer is Bart's father. Now I'm asking Homer is Bart's mother. And a lot of things that you take for granted in English, we can use in this little language, which is kind of cool. So if I say Homer is not Bart's mother, the system knows what I'm talking about. I can even use double negation, so Homer is not Bart's mother. And if you can wrap your head around that, it makes sense. So I can also ask questions that involve variables. So here I'm saying, who is Bart's father? If I ask the system to tell me, oops. Come on. Turtles all the way down. Gets you anytime. So, okay, X is Bart's parent. Give me 2 answers. And so on. You kind of get the point. So let me see. So Lisa is smarter than X. Okay, let's get back. So, okay. I've shown you all these cute examples, but where do you fit in this stuff? What can OMeta do for you? So, one thing that you can do is, so domain-specific languages can really help you out, actually. And the problem is that it's, at least a problem to me, is that it seems like the computing community is kind of split into 2 groups, at least in my mind, as in programming languages guides. There's the programming languages people who know how to implement programming languages and domain-specific languages and all this good stuff. And then there's everyone else, and these other people are doing really, really cool stuff, but maybe they don't have the expertise to build things like domain-specific languages. And I think that they could really benefit from these things. And so, especially because as a programming languages researcher, the problems that I think about all the time have to do with programming languages, right? And so most of you really don't care about that. But you're working on interesting stuff, and you probably have a bunch of problems that I have no clue about. And maybe you have an idea, you know, maybe I could build a DSL that'll make this problem go away and so on. Well, we've had experience with other people, we've seen other people use OMeta when they've had pretty much no compiler's background. And they've been able to implement languages with fairly minimal effort and kind of expenditure of time. And I think that's a pretty cool thing. So that's one thing that I'm going to do for you. Another thing is, so you love Smalltalk, you write all these cool applications, but maybe your users don't know how to use Smalltalk. And so for a Smalltalker, everything is open-ended and great, right? You see this application, you kind of want to automate part of it. Well, maybe you just open up a workspace or whatever and start, you know, writing some code to make the application do whatever you want it to do without clicking buttons or whatever. Well, your users, chances are your users are not going to be able to do that. They're not going to be expert Smalltalkers. And so one thing that you could do is build these little languages that enable your users you know, in a very non-scary way to automate your applications. And that could be a pretty nice value added. And so, enough about that. So this is what I'm going to do in the rest of this talk. First I'm going to give you a brief overview of OMeta, and I'm going to tell you a little bit about how it works. I'm going to talk about its notion of pattern matching, which is the central concept of this language. And I'm going to talk about OMeta's OO features and how it can help you as a programming language implementer, things like that. And I have to be honest with you, I guess maybe this is going to get overly technical. But I hope that you'll stick with me through this stuff, because in the sort of third part of the presentation, I'm going to show you a lot of this stuff in action in the latest and greatest version of OMeta, which is OMeta on top of JavaScript. So anyway, try to hang in there, and if it seems like things are just too boring or whatever, just raise your hand and let's speed it up and get to the good stuff. So before I go into details on OMeta, I should probably talk a little bit about the way things are done traditionally in programming implementations. So a traditional implementation uses a bunch of different tools and techniques. So it's not, I mean, yes, the Squeak compiler is already in Smalltalk or whatever, but most people use things like Lex and Yak for doing lexical analysis, parsing, or since you guys are from the Smalltalk community, you use things like TGen or SMAC. And there's also this thing called Visitor Design Pattern that you guys use all the time. Well, people use this design pattern for doing things like transformations on parse trees, and also code generation, albeit sort of naive code generation, where you just sort of say, hey, this is what the abstract representation of the program is. We're just going to go and translate this into something that's executable without worrying too much about performance. So people do this kind of thing all the time. And I guess the thing that I was talking about before is that this kind of approach is not going to work for us for several reasons that I already went into. And so OMeta has a different take on this. It views all of these stages in compilation as instances of the same problem. Okay, so it's like you can think about, well, basically this problem turns out to be pattern matching. So lexical analysis, is this thing that happens when you take this basically a string or a stream of characters, and you're creating another stream, which is a stream of tokens, right, which is easier to deal with and so on for the parser. Well, you can think of that as just a process that finds patterns in the stream of characters and produces a stream of tokens as a result. And similarly, you can look at parsing as a piece of code that's finding patterns in a stream of tokens to produce parse trees. And then you have all these visitors and transformations on parse trees, which include optimization and so on, which are really about finding patterns in parse trees to produce other parse trees. And there's also code generation, which is just, if I find this pattern in my parse tree, I'm going to create this bit of code that we can do code generation. And so, why the heck would we try to use pattern matching for everything? Well, one of the reasons is that it turns out it's pretty simple as a foundation for the whole implementation. And it means that whoever is going to be learning this kind of approach has a lot less stuff to learn, which lowers the learning curve to programming language implementation. And it's also great for extensibility. So if you think about this kind of approach, where you're using a bunch of different tools, well, maybe TGen and SMAC provide a certain kind of extensibility mechanism, right? Or maybe they don't. I don't know. I haven't actually used these things. I've used other tools that are similar. So, but the fact is, sometimes you end up having to pretty much take the code that say, okay, so I have a JavaScript implementation, and I want to experiment with adding some feature to JavaScript. Well, one thing that I can do is take all of the source code that I already wrote to implement JavaScript and then modify it in place, right? Or maybe if I have different parts of the system using different tools, I'm going to end up having to use whatever extensibility mechanism hopefully is provided with those tools. And so it can be a mess and a hassle. So the thing about using one kind of formalism or one tool for everything is that, well, especially if it's object-oriented, and you guys all love object-oriented programming like I do, every part of the implementation, so the parsing code, the traversals on the parse trees, the code generation, they can all be extended using the same mechanism, which means basically for us, inheritance, overriding, things that we use on a daily basis, which is actually a pretty cool thing. And I'll show you examples of this. So sometimes I tell people about OMeta and how it's based on pattern matching, and then they say, well, I know how to program, say, ML. And ML has pattern matching too, so why do we need OMeta? And so if you think about ML-style pattern matching, well, it's great for doing things like tree transformations, but it's not so great for lexing and parsing. That's why these people use MLX and MLYAC, or their TGen, or whatever. Right? So we don't want that to be the case. We want our notion of pattern matching to be a natural solution for all of the stuff that we want to do, which includes parsing. And so this is why OMeta is based on something called parsing expression grammars. And what is that? Well, that's a recognition-based foundation for describing syntax. And that sounds pretty fancy, but don't let that scare you, really. All it is pretty much a nice framework for writing recursive distinct parsers. And so there's only, if you've used these parser generators, when you say, an expression is an addition expression or a multiplication expression, things like that, the OR operator that you're using there is called a non-deterministic choice, right? There's no priority in that choice operator. These things work like recursive descent parsing, so the choice operator is ordered. And so when I say, an expression is a plus expression or a times expression, I'm going to try out the first thing first. If that fails, I'm going to try out the second thing after I've backtracked appropriately. And what's so cool about this? Well, one thing is that there's no way for you to have ambiguities in your grammar if you write it using something like this. It also makes the behavior of your parser really easy to understand and debug. And you never get things like shift reduce conflicts or whatever, which if you've used these tools, maybe you've come to hate. So this stuff also supports backtracking and limited look ahead. And also this really handy thing called a semantic predicate, which is, so anywhere inside a rule in my grammar, I can write an expression in some underlying programming language like Smalltalk. And so that's the syntax for that in OMeta. And what I'm saying there is, make sure that x is equal to y. And if it isn't, fail this current thread that I'm on, right? So if I'm trying to parse something and I have x and y bound to something, then I can test their values. And this kind of construct really adds to the power of this approach. So here's what one of these parsing expression grammars looks like in OMeta. And I'm using the syntax of the Squeak-based version of OMeta. So here's a little grammar for a little language of expressions. Right? So a digit is a character from 0 to 9. A number is basically a bunch of digits, and an expression is an expression followed by a plus, followed by a number, or just a number. And so this on its own is enough to give you a recognizer for this little language. But recognizers are really no fun because they don't let you do anything, right? They're just going to say, yes, your input is valid, or no, it isn't. So let's make this into a parser so we can do some neat stuff with it. So one thing that you may want to do for writing a parser is name the particular things that we're matching here, right? So if I match a digit, maybe I'm going to call it digit D. If I'm matching an expression, maybe the first part of the expression I'm going to call E, the second part I'm going to call N, and so on. And the reason why we do that is so that we can use those values in these things called semantic actions, which produce useful artifacts while the program or whatever thing it is that you're pattern matching against is recognized. So this little bit of code is producing parse trees. And so, and we're going to see what these parse trees look like next. But anyway, so this is giving you the same kind of power that that these parsing frameworks or parser generators give you. All right. So, but we're not only interested in parsing, right? And pegs, these parsing expression grammars, only operate on streams of characters. And so we don't want to put up with that limitation. So OMeta extends that idea by operating on streams of objects, right? So, so there's a special rule called anything, which is going to take exactly one object out of your input stream, and then you can do whatever you want with it. And it turns out that that is enough when you combine it with these semantic predicates to do pretty much everything that you ever want to do. And of course, the code is going to look ugly. If, for instance, every time I want to match the character C, I have to say anything, then match the result to C, and then make sure that C responds, true to his character or something like that. It's pretty awful. So we have shorthand or special syntactic sugars for matching things like strings, symbols, characters, numbers, and listy objects, which are things like arrays, ordered collections, and so on. And these things, of course, can be nested inside list objects. So you can have a list pattern that itself has a list pattern inside of blah, blah, blah. So we're getting through this. So anyway, here's an example of using that generality that I just talked about. So we've got a parser that we wrote a couple of slides ago that produces parse trees that look like this stuff that you see in the bottom, right? So this is a parse tree that's made up out of a discrete array or a Smalltalk array. So the first element in these arrays tell you what kind of parse tree node it is. So this thing is a plus, where the first operand of the plus is itself a plus expression, 1 and 2 as operands, and then the whole thing. So I'm adding 1 to that 3 together, right? And that parse tree tells you what the precedence looks like. And so what this little rule, this eval rule is doing, is pattern matching on this parse tree to produce the result of evaluating the expression. So if I'm evaluating an object that looks like this plus parse tree, I'm going to evaluate recursively both of the operands. And then once I've done that, the result is just going to be the result of adding those two things together. Otherwise, I'm just going to take whatever object I'm trying to match against, bind it to n, and then make sure that it's a number. And if it is, then the result of evaluating what number is just there. And that's enough to evaluate these little parse trees. So here is the original parser we wrote. And I've said that OMeta is object-oriented. So you should think of these grammars as like classes, and the rules as like methods of these classes. And so the rules are not sort of free-floating. And you can see that once you start thinking about things that way, it makes sense to name one of these grammars. So this grammar is going to be called my language. And if we're going the OO route, then it makes sense for a grammar to have a super grammar. And it turns out that in OMeta, every grammar inherits eventually, transitively, from the grammar called OMeta, which provides basic rules like anything, digit, and a bunch of other useful stuff that we see later. And so one of the benefits of doing things this way is that it's really easy, using stuff that you already know from doing your Smalltalk programming, to extend these languages, right? So when you have a grammar for my language, you can make a subgrammar called my language plus plus that extends this little language of expressions with, say, minus expressions. And so here I'm overriding expression in my language, so they're saying minus, and then if that pattern doesn't match, then I'm just going to invoke the super grammar's version of expression. Okay? Any questions so far? All right. So, and like I said before, this kind of inheritance-based approach doesn't just work for your parsers, it works for pretty much everything inside the language implementation, which is really good. Now, one thing that really gets to you when you're writing a bunch of grammars is that there tends to be a lot of repetitive work. So this is a rule that matches a digit. And you can think, well, this is fairly okay, right? I can write this quickly, and I'm not going to make a mistake doing it. But think about a rule that matches, a character. It's pretty awful. Or a rule that matches, say, just a letter. So these things can be error-prone. They can be tedious to do, or whatever. So some big implementations allow you to get around this problem by saying, well, I'm going to give you a shorthand for defining a range of characters, kind of like regular expressions. But in OMeta, we do things a little differently. We think that this kind of thing puts the power in the hands of the user a lot more. And that is that our rules can take arguments. And so here, this range rule that I'm defining below is taking two arguments, A and B, and what it does is it takes out of the input stream one object, and then it only succeeds if that object is greater than or equal to B, greater than or equal to A, and less than or equal to B. So it's in between A and B, the endpoints of the range. And if that works, then I'm going to return the object. Otherwise, I'm just going to fail. Right? So you can rewrite this whole agent rule into a call to range, passing in the appropriate arguments. Right? And this kind of expressiveness is inspired by parser combinator libraries. And there are other systems that have this kind of thing, including Gilad's really cool Newspeak parsers, which you probably heard about a couple days ago. So there are actually a lot of similarities between this stuff and what Gilad is doing. So anyway, rules can take arguments. We've already seen that. And it turns out that these arguments can be other rules too. So some rules can be higher order rules. And why would you want that? Well, so here's one thing that happens pretty often when you're writing one of these implementations. Okay, you end up having to write rules that are used to find, say, to match lists of formals for arguments or connection, lists of arguments which are passed to a function or something. And so the first one is just a list of names, the second one is a list of expressions. These things happen over and over again. You end up having 20-something different rules for things like this. And it's a lot of repetition. It's really annoying. So using OMeta's parameterized rules and a special rule called apply, which is kind of like Smalltalk's perform method, you can write a rule for parsing any kind of list, which just takes the kind of list that you're parsing as an argument. So you can say a list of P is obtained by applying P, and then trying to apply a bunch of times, trying to match a comma character followed by an application of P as many times as you can. That's what the star is. It's called a clean star. That's from the So you can use that wherever you want. And so here I can rewrite formals and args to calls to this stuff. So here is, I think, the last one of these crazy language features, and then we're going to get to the good stuff. So be great. And I'm going to start out with a little real-world example to motivate this feature we're going to talk about. So suppose I have a parser for OMeta and a parser for JavaScript. And I want to create a language that's the union of these two languages. Okay. So maybe I want to use this language in a workspace kind of interface, where I can either type an OMeta grammar or a JavaScript expression and just tell it to evaluate on the fly. Well, since we have this object orientation and only single inheritance, you're left with a choice, right? If you want to write a parser for this kind of language that's the union of these two languages, one thing you can do is inherit from the OMeta parser. But then you end up having to duplicate most of the code in the JavaScript parser. Likewise, you could choose to make a subgrammar of the JavaScript parser, but then you have to duplicate all of the work in the OMeta parser. And all of this duplicated effort is worse than just tedious. It actually creates a versioning problem, because later on, whoever wrote the OMeta parser, me maybe, is going to go and change the language a little bit. And it would be nice if the union language would just reflect those changes automatically, right? Benefit from those changes. And this is not going to happen if you, say, do it this way, because you had to copy all of the code in the OMeta parser in the first place. And so, and even if OMeta supported multiple inheritance, that would be a pretty awful way to solve this problem, because say you can inherit from both of these grammars. Well, now you're going to have all sorts of rule clashes, and maybe the notion of an identifier in these two languages is slightly different, and one of them is going to win over the other, and then something's going to break, right? We don't want to have to deal with that kind of complexity. So the solution in our system is called foreign rule invocation. which is a way for a grammar to kind of lend its input stream to another grammar temporarily, and say, okay, you try to do your thing with my input, and then give me the result. So this lets you implement the OMeta JavaScript parser by first trying to invoke, first trying to say, here's my input stream, OMeta parser, try to give me a grammar out of that. And if that fails, I'm going to pass the JavaScript parser. Well, try to parse a statement out of this input. And this kind of thing is pretty neat because it lets you compose grammars without having to worry about name clashes. And it's kind of a neat feature for modularity. So, and it allows you, I guess, people have been talking about mashups, application mashups, in the context of JavaScript lately. And this term gets used a lot. Well, this kind of thing lets you create language mashups, which are pretty neat to programming languages. So, now we're going to get to some neat stuff. But before we do, I should say that I should reiterate that we have several versions of OMeta. There's a version that runs on Squeak. There's a version for Cola. There's a version for JavaScript. And we're actually the user community for this stuff is starting to build up. And ports to different languages are starting to pop up, which is really nice. So some guy that I don't even know made something called OMeta, which is OMeta for Python. Someone's working on a Ruby implementation, and someone's working on a C# implementation. I feel bad for that guy. And actually, someone from the Smalltalk community actually ported the OMeta Squeak version to VisualWorks. So if that's your favorite Smalltalk, you can start using it too. So anyway, the point I should make is that each one of these versions of OMeta has a slightly different syntax. And the reason for that is because, say, lists look different in JavaScript than they do in Smalltalk. So it makes sense. It makes for better language integration if the OMeta JavaScript version uses special syntax that looks more like JavaScript to match lists and arrays. So, and also another difference is that whatever language OMeta is sitting on top of, that's the language that's used to write semantic actions and semantic predicates. Right, so I said we're going to be focusing on OMeta JavaScript. And this is starting to sound redundant, but first, these messages. Right? Sometime last year, a co-worker of mine at Viewpoints, his name is Takashi Yamamura, a lot of you know about him, does really cool stuff in Smalltalk. He decided to write a web page that is pretty much a workspace-style interface for programming in JavaScript. And this thing runs in any web browser and works like a wiki, so people can go and create a new web page and use this workspace, whatever, and save it and share it with other people. So I thought, wow, that's a pretty brilliant thing because it runs anywhere. Anyone who has a browser can try this out. And I thought, it's kind of evangelizing the Smalltalk flavor to people who may not be so open to it. And I thought it was great. And this is actually the inspiration for this JavaScript version of OMeta. Because having had implemented JavaScript before, I already knew the language pretty well. Sure, it's no Smalltalk, but it's a nice little dynamic language. It has things like first-class functions that are properly closed over their environment, things we call these closures. It's very late bound. It has a really useful eval function that lets you evaluate and compile code on the fly. And recently, there have been huge performance improvements. So the new JavaScript in WebKits runs at about half the speed of Squeak. So you can do some pretty neat things with it already. We've seen Daniel Smiley here. And maybe the best thing about JavaScript is that it's everywhere. Everyone, your grandmother's computer has a web browser that runs JavaScript. So while it may not be your language of choice, it's definitely a force to be reckoned with. Especially when you realize that you don't have to program it. JavaScript just might be the world's best assembler. So if you use it as a target for code generation, you can really get a lot of interesting stuff going on. And there's this book that I can't say enough good things about, written by Doug Crockford. This guy's like the #1 authority in JavaScript. And his book is called JavaScript, The Good Parts, and it has really thoughtful commentary on the design of the language. And it's kind of, I guess he's a programming language geek himself, and I recommend it to anyone who's interested in JavaScript. I know I'm not getting commission. I'm just excited about it. So I'm going to switch to the web browser a little bit, and hopefully this stuff will work well. You guys can't read that, right? Does this work for everybody? Okay, great. So this is the OMeta webpage. And it's pretty much, at first glance, it's kind of like a re-implementation of Takashi Uemiya's JavaScript workspace. So this is text and stuff. It's just a little text area in HTML. But I can go and type some JavaScript code and do a Control-P and get the results, right? So you evaluate things on the fly, just like that. So I'm creating a function and applying it to 5 and get 6, and so on. So this is really a Smalltalk workspace. And this is no improvement over what Takashi had done. But the thing that I realize is that there's no reason that we have to put up with JavaScript for something as cool as this, right? So this wiki idea is really, really neat. And it's probably going to be even neater if we can insert some interaction between the code that you write and the code that gets executed. And in this thing, that's implemented in a function called translate code. So if I evaluate that, you see the source code for that. You don't have to actually understand that. The idea behind it is this. Every time I say print it or do it, I'm going to take a string and pass it to translate code. And that guy can go and generate any JavaScript it feels is right for this code that you wrote. And then that's what gets evaluated, right? So you can, so you've already seen that this version of translate code lets me type JavaScript, which is good. I mean, it might as well be the identity function right now, but it turns out it isn't, right? It's actually it's a language mashup, like I talked before. It's this thing that's the union language between OMeta and JavaScript. So I can actually type, let me see if I can make this bigger. So I can type OMeta M. This is a grammar called M, and I'm creating a rule called ones, which is 0 or more ones. And if I select that, I can evaluate it, and it works. So now in JavaScript, I can ask this grammar to match this list of ones with the ones rule, and I get the result. So OMeta is actually running inside this web. Sure, but that's a silly little example. So I'm going to show you some of the things that you've seen in this talk today, in a more lively fashion. So, okay, here is one of those little languages of expressions. So this is a recognizer for a language, and so I can, if I select the code for this thing and evaluate it, I can ask it to match the input 6 times 4 plus 3, and it doesn't complain, which is good. if I type some garbage in there and try to match it, it throws an exception. It says, oops, the match has failed. So it's doing what a recognizer does, right? It's just validating the data. So here's a different version of this thing that instead of just recognizing, it interprets these expressions. So I can select this code and tell it to invalidate times 4 plus 3, and I get 42. Which is the correct answer. So okay, here is a different version of this stuff that's actually a parser. So so now instead of evaluating these things, I'm parse tree nodes. So if I say tree is the result of matching this same input with expression, I get this sparse tree that okay, I get the sparse tree that's correct. So here is something similar to what we saw in the talk, which is an interpreter for these sparse trees. It's a little bigger than the one we saw, but the idea is the same. So it validates the sparse trees. We can do things like compilers, and I have a bunch of examples of this stuff. I think you get the point. So I'm going to do some less videos. So one thing is that, so I've talked so okay. I've talked about source-to-source compilation a little bit and why I think that's a great idea. And so let me give you an illustration of that. It's a little more vivid. So this file over here is a library written in JavaScript that implements the semantics of Prolog. Okay? And it's about 70 lines of code. So you have some code here for unification, you have some code here for backtracking, and so on. It's pretty straightforward, but in order to use this stuff, you have to write some pretty hairy code. And so this is, I don't know if you've seen the Prolog code to enumerate all the natural numbers, the piano arithmetic kind of thing, but this is it if you use this library. It looks awful, but it's nothing you would ever want to write. And this thing over here is the kind of Simpsons family example where you're sitting there teaching it what a grandfather is, and then ask questions. You never want to write something like this. So most programming languages that we enjoy using are really good for describing semantics, but then they may not be so good for using those semantics. So when you have this source-to-source compilation approach, then you can put a really pretty face on top of these things. Really, with minimal investment. And so this maybe 12 lines or so is a parser for Prolog. Granted, it's a subset of Prolog. It doesn't have things like lists, but you can build lists out of Prolog predicates. And so that doesn't matter too much, but it's enough of a subset to be interesting. And so so here I'm evaluating the code in the Prolog library, so I loaded all that stuff up. Now I'm teaching this browser how to understand Prolog syntax. And in here, I'm asking my Prolog translator to evaluate this. So the question I'm asking is, give me all x's such that x is a natural number. And the rules that I'm giving it is that 0 is a natural number, and that the successor of x is a natural number if x is a natural number. Right? It's a fairly standard Prolog thing. And if I select this code and say do it, I see that 0 is a natural number. If I say, well, give me another answer, it says successor of 0 is a natural number, and so on, until infinity. Eventually, you can say I'm happy, and it stops. Here's the family example where in Prolog I'm saying that Abe is Homer's father, Homer is Lisa's father, Homer is Bart's father. Then I have what grandfather means, and I'm saying, tell me who is the grandfather of whom, and it says Abe is Lisa's grandfather, Abe is Bart's grandfather, and there are no more answers. So, working Prolog and say 100 and somewhat lines of code, not too bad. So let's see. Okay, this one is fun, so just gloss over it. So this is a logo in OMeta. So this is the definition of logo and then a little logo program that teaches the system how to draw a spiral and says go. By the way, I took this snippet of logo from the Wikipedia page on logo, so I didn't make it up. This is a real logo. So if I select all this code and say value, it's doing logo in Robertson. You can imagine it would be much cooler to run this stuff inside the library code, right? Some really neat things. And this is something we're going to be exploring sometime very soon. So, now we'll see something a little more serious. So this code over here is a source-to-source JavaScript compiler. And what it does is I can parse JavaScript, then I have these nice little parse trees, and then I have some code that compiles the parse trees back into JavaScript. So it's like an identity compiler, right? You just take one program and you spit out the same program. Why would I want this? Well, once I have something like this, I can easily extend JavaScript with whatever thing I'm interested in. So here is a little project called Extended JavaScript, which loads up JavaScript compiler, creates a grammar that extends this original JavaScript grammar, and teaches it a new kind of statement called save, right? Which is something that, so here's the kind of code I want to be able to write. Say hello world, and then that should pop up a little window that says hello world or whatever. It's really trivial, I know, but you get the point that this thing scales up to arbitrary complexity. And so I'm going to load up this grammar, and then I'm going to save the old translate code function and redefine it now to use my new JavaScript, which means that now, on the fly, I've changed the language that's understood in this workspace. So I can still do JavaScript stuff. 1 + 2 is still 3. But if I say hello world and say do it, I get popping up. It's really, if I change it back and then try to say world again, it says parse. We've taken language that's a static thing, right? JavaScript wasn't made to be extended. And just writing this little source compiler, the language more now than what I was working, which I think is a really powerful idea. So now I'm going to be done very soon. So So this quarter is a really interesting topic. So Alan came, obviously viewpoints, but he's also an advisor at UCLA. He teach a class in programming language design, and he come in and speak. So this is really, really neat. And one of the things that we wanted to students, a lot of them haven't looked at compilers or bootstrapping or anything like that that has small we hold deep parts. We think it's cool to have an example of language to show them, to tell them bootstrapping is really. So here is a little bit of JavaScript code, and it fills up this little page. But what it does is it defines a semantic like OMeta. And here, grammar in OMeta that parses an OMeta-like language, generates some that uses the slide nodes to make it useful. And so I'm going to select this stuff and say good. Now, Now we're going to see if this works. So this language looks a lot like OMeta. And I'm going to have this little example stored in the screen. So this little example is just a parser for expressions. And now I'm going to tell this language translator called the Meta2 translator to compile my grammar. And I get an object. And then if I tell my grammar to match 6 times 4 plus 3, I get a parser. So this stuff is working already, right? So I've made, in very few lines of code, I've implemented a language very much like OMeta. And then the students go, wow, this is really cool. I'm feeling more powerful already. But the really neat thing is when you can take that language that we've just defined and implement a compiler for itself, in itself. So here is that compiler. It's a little bit bigger than our expression language, not much. And so I'm creating a new meta translator from parsing that grammar, and I'm gonna now I'm gonna try to parse the same grammar of expressions that we saw before with the new parser, and I get a result, and it still works. So now this version that was implemented in the language itself worked. But if you really want to test the thing, you want to compile this fairly complex compiler written in the language itself, using this new version of the compiler that was written in the language itself. It's kind of like a stage 2 of the bootstrapping. And what we're doing now is compiling the same little example, and darn thing still works. And so with Bootstrapped, we've done this thing in a fairly easy to understand way. And so the students got a kick out of this example, and some of them went on to do similar things. So, and one thing that's very similar to it is the OMeta compiler, which is implemented in itself. And so here is a web page with the OMeta compiler. So this is the parser part of it, and this is the part that translates the parse tree nodes to JavaScript. And this page basically shows you the same kind of bootstrapping idea, but for OMeta. So one thing that was really cool to see was, so we taught the students how to use OMeta, and then they started playing with this stuff, and they said, well, I have some ideas that I'd like to try out for OMeta. So what some of them ended up doing for their project was they took this piece of code, and then they extended OMeta with whatever feature they thought would make their lives easier when they were implementing the language. And they tried things out, and so I thought this was a really cool experience, and they really enjoyed doing this, which it's been like a really nice user story. And so here is the very last example, and then we'll do questions. So it's kind of an offbeat example, but some of the students in this class were interested in music, and they had so a couple of them had this idea. Well, you know, it would be really cool if I could make a programming language for describing music. And I'm going to use OMeta to do this, and I'm going to do that in the web browser. So we got together and we looked into the feasibility of this, and it turns out that it is possible to generate MIDI files from a web browser play. And so it took a couple of days to figure out how to do that, but they managed to do it. And so here is a little example of their language. So you can question their language design. Maybe this is not extremely readable. They thought it was cool, and they did some pretty amazing things with it now. So here is a big string that is written in their language. And by the way, I should say that these guys had never written a compiler before. And they were first-year graduate students. So I'm going to select this big string that describes happy birthday in their language, and then I'm going to use, and I'm going to tell their implementation to compile this, and we'll see what happens. And we'll see what happens. Okay, hang on. Something. So that MIDI file was generated dynamically from this little program. I think this is the coolest. And it didn't take them, I think, once they learned how to do it, it didn't take them more than years. And I was pretty happy. And that, I guess I should. Turns out I had. Okay, so done with all the demoing. I want to say one more thing about JavaScript. So I said that it was everywhere, and I wasn't exaggerating. A couple of days ago, I went to a friend's house. And this guy has a lead, works for Google. Apparently everyone who works for Google has a lead. I spend all of their time playing games. So this guy was playing around with his Wii, and he showed me that the Wii has a web browser. And it turns out it's just a version of Opera. And this web browser has a full JavaScript implementation. So I tried this out, and I typed in the OMeta.js URL, and lo and behold, it worked. So now, this is a huge thing, I think, because it means that anyone with a $250 computer can learn about programming language design and implementation, right? So these guys, so I'm gonna forget Guitar Hero. I'm gonna design languages and do the next 10 minutes. So anyway, that's pretty much all I have to say today. If you want more info, you could read the paper that I had with Ian in last year's Dynamic Languages Symposium. There's also a new mailing list for OMeta, and that's the URL to sign up. We have about 80 users now. The community is starting to pick up. And there's also that JavaScript, OMeta JavaScript wiki that I showed you. So you can go online and create your own OMeta projects and make them available to the rest of the world. And I encourage you to do that. And you can also, to find out more info, I don't mean that as a mandate or anything, but you can ask me questions.
Where did the name come from?
So one of the inspirations for this stuff, so a couple of years ago, I'll give you a tiny bit of background. I'm a graduate student at UCLA, and I took a class with Alan, and I thought it was really cool, and I tried to impress him, and because I wanted to work with him, Alan Kay, that is, and so it seems to have worked when he hired me for an internship at the time, and the first thing he did when I started my internship, because I was interested in compilers and stuff, is he showed me a couple of projects from the 70s that were about doing compilation in easier ways than we do now. And one of them was called Meta 2 by Val Shore in 1964. And this thing was a self-describing compiler. It was beautiful. A 10-page paper changed my life. And so that's one of the that's one of the biggest influences for Meta. And so that's where for Meta 2.
Do you have any idea how the visual works on these?
So can you repeat the question?
Visual works implementation for that?
What about it?
How up to date would that be?
Oh, so, all right.
I can answer that kind of.
Okay.
The last published to store was on May 22nd.
Okay, so that sounds, so the question was, how up to date is the visual works implementation of OMeta? And this nice gentleman over here said that it looks like it's from May the 22nd or something like that. But I have a confession to make, and that is that the latest and greatest, like the state of the art in terms of OMeta is in this JavaScript implementation. And my plan for the next few weeks is to backport all of this work into Squid. And at that time, this very nice Japanese guy, Masashi Megala, I'm probably butchering his name, who did this work for Visual Works. I'll talk to him and see if we can update that to have the latest and greatest.
A post from him on June 17th. Masashi Umezawa.
Masashi Umezawa. So I got the name wrong. You get the idea. He's Japanese. A really nice guy. More questions?
So back in the 70s, I also, just before doing Smalltalk, I did also compiler stuff. So what are the limitations in OMeta in the terms of the class of grammar to be recognized?
So the foundation for this thing called parsing expression grammars that OMeta is based on.
But that's much newer than I did. So that's 20 years younger than I left on.
Right, so, but the thing is that this technology was based on something that's fairly old called TDPL, which was work done by Berman, I think. And so, I mean, it's pretty much a rehashing of that work done by the newer stuff, the pegs, that's work by Brian Ford at MIT. And so, the thing is, the point I'm trying to make is that this foundation for describing syntax is actually more expressive than a lot of things that people use today, in industrial strength kind of compiler writing frameworks. It's definitely more expressive than context-free grammars. And so there's a lot of languages that you can implement parsers for using pegs that you cannot write context-free grammar. So it's, as far as limitations, I've done a lot of experimentation with this kind of stuff, and I have not kind of hit the ceiling yet. I'm hoping I won't for a while, but if I do, that would be a really interesting problem to have.
So one of the most important problems was in some languages you have to declare a variable. You have to make sure that the variable is declared before.
Yes.
So that goes to the point that you also have to put things down to the tree.
So the way I do that in OMeta, and I've implemented languages with variable declarations. Even JavaScript requires that to be done properly, actually, because JavaScript has this really weird way to do scoping. And the way it works is, if you have a variable declaration anywhere inside the function, that variable is local to the whole function. So it's not enough to just compile a function sort of step by step. You have to actually extract all the variable declarations from the function and pull them out to the top level of that function. Because even if you have like if blah blah blah, and then inside the true block, you have some variable declaration that's actually scoped outside. And so the way that I implement things like that using OMeta is by writing all these visitors in there. So I first implement a parser for JavaScript, and then I have another kind of pattern matcher implemented in OMeta that finds variable declarations in a parse tree generated by my parser. And once those variable declarations are found out, I decorate the parse tree with these declarations in the right place. And then I can compile after that point. And so you can do multiple passes over the same data. So it has worked out pretty well. And you can, by the way, this is the same way that there are some optimizations that I implemented for OMeta for it to run reasonably fast in the browser. And those also have to do with rewriting the parse tree of OMeta rules and stuff like that. And I did it all using the same kind of thing. Yes.
You had a tutorial, but it looked like it was in a file on your laptop. Is there a tutorial that's available on the web?
Yeah, absolutely. So if you go to this page I've been showing you, this is a local version of the OMeta.js wiki. But if you go to the page that I told you about, or just Google OMeta.js 2.0 or something like that, there's a 1.0 that I'll mention in a second. But you can go up here in important information and find the OMeta tutorial, and it'll just load up. So a couple of words about the previous version of this OMeta.js stuff, which may be interesting to you. So JavaScript has a bigger grammar than Smalltalk does. And when I wanted to get this stuff going, I was interested in I had written Smalltalk parsers before. I had done JavaScript too. So, but the thing that I chose to do in the beginning with OMeta.js was to forget about JavaScript altogether and first implement a translator from Smalltalk to JavaScript. So I basically made a workspace like this that understood JavaScript, that understood Smalltalk. So you type your little Smalltalk programs and loops and so on. And then I extended that with OMeta, and so you could write the semantic actions in Smalltalk. So it was basically a JavaScript-based implementation of the Squeak version of OMeta. And so you may be interested in looking at that, even though it's kind of outdated. So, more questions? We still have about 10 minutes maybe. Okay. We'll talk about this to death soon. Thank you so much.